In this portion of Chapter 12, we're going to look how electrophilic additions occur with conjugated dienes. So a conjugated diene is a species that has alternating single and double bonds. So this is a conjugated system. It is the simplest conjugated system where we see a double bond, a single bond, followed by another double bond. So these are these alternating single and double bonds. And it's what we call a conjugated system. This is a conjugated diene because we only have two alkenes that are separated with one single bond. With conjugated dienes, the reactions that they undergo with the electrophilic addition, we end up getting a mixture of products. The mixture of products that we achieve is going to be what we classify as a 1,2 addition, as well as a 1,4 addition. So let's look at a reaction of our conjugated system and how we will achieve the 1,2 versus the 1,4 addition. So with our conjugated diene, I'm just going to look at it in the presence of our strong acid. So it's the same electrophilic addition that we've looked at previously. And what we're going to see is we do get our two products. One of our two products is going to be our 1,2 addition. So with our 1,2 addition, what we're going to be looking at is we're only going to be taking advantage of one of the double bonds, and we will see an addition of the hydrogen to the 1 position and an attack of the next nucleophile, the bromide, to what we're going to classify as the 2 position. So this is what we refer to as a 1,2 addition. We ignore the fact that there is a second alkene. We focus on one of the alkenes and we see the addition across it. So in that 1 and that 2 position. But we also see our 1,4 addition, and in our 1,4 addition, we're going to see a change in where we are going to add the second nucleophile that comes in. So with this one, I'll continue to number along 3 and 4. So in this reaction, what we see is we add to position number 1 that initial hydrogen, but then the second nucleophile is going to come in and attack at position number 4 instead of position number 2. And through that process, we see a change in the double bond as well. So you'll notice that now the double bond is between carbon atoms 2 and carbon atoms 3. So in our conjugated system, we will produce both of these products, the 1,2 addition and the 1,4 addition. Please recognize that this 1,2 and 1,4 that we're talking about has nothing to do with nomenclature. All as it is doing, it is taking this diene, this conjugated diene system, and we're numbering it 1, 2, 3, 4. So 1 and 2 is one of the double bonds. The 3 and 4 is the second double bond in that conjugated system. And the 1, 2, and 4 are telling us where we are doing our addition to. Where are the species adding? So for the 1,2 addition, we're adding the hydrogen in position 1. We're adding the second nucleophile, the bromide ion, in position number 2. For the 1,4 addition, we're adding the initial hydrogen in position number 1, and we are adding the halide in position number 4. So keep in mind this discussion of 1,2, 1,4 has nothing to do with nomenclature. So let's look at the mechanism on how we end up converting or producing both the 1,2 and the 1,4 products. So I'm going to start with my conjugated system, and we're going to react it with the electrophile. So one of the alkenes is going to react with the hydrogen, the electrophilic hydrogen, breaking the bond between that hydrogen and that bromine to initially produce for us our carbocation. This initial carbocation that we have will react with the bromide ion, just like we saw in our previous sections, to produce for us that 1,2 addition. So from here, what we have to recognize is with this carbocation, we have an allylic carbocation. And remember, those allylic carbocations are going to be stable for us because they have resonance associated with them. And through our resonance, we can move that carbocation to the end. And it is going to be this second resonance structure that we can draw that will react with the nucleophile to produce our 1,4 product. So what is different with our conjugated system is that we have a resonance stabilized carbocation intermediate because it is an allylic carbocation. So through the resonance structures is where we see that second product, that 1,4 addition product being generated. So again, we will produce both of these products. One of them is through the initial carbocation that we generate. The second, the 1,4 product, is through the resonance structure that we have with the allylic carbocation. One of the things that we do have to watch for is when we have asymmetric conjugated systems. When we have asymmetric conjugated systems, we end up getting out a large mixture of products. So remember, every conjugated system will produce two products, the 1,2 and the 1,4 addition. But if we have an asymmetric system, we can get up to 4 different products being produced. So if we look at an example, I have a conjugated system. It is an asymmetric conjugated diene. I'm going to put it in the presence of water and sulfuric acid, and we end up producing 4 different products. So these are the 4 different products that we have. I would encourage you right now to pause this slideshow for a minute and see if you can walk through the mechanisms on how we actually produced all 4 of these different products. If this were a test question, I would expect you to predict all 4 of these different products, as well as being able to draw the mechanisms for them. So looking at these 4 products, the first 2 products come from the same initial carbocation, and these are going to be the initial carbocation that is going to react with the carbon or the alkene that is on the left-hand side. So the first one is going to be the 1,2 addition to that initial carbocation, again the alkene that we're reacting on the left-hand side. The second one that I have drawn is coming from the 1,4 addition of that initial tertiary carbocation that we have. And recognize that this is a tertiary carbocation, so it's a nice stable carbocation. It's still allylic, so we can still go through our resonance stabilization. The second 2 products that are the third and the fourth products that I have drawn here are going to come from a reaction of the alkene that is on the right-hand side. So this would be the initial carbocation that we would form that is on the right-hand side of the molecule. The first one that I have drawn again is coming from the 1,2 reaction of the alkene on the right. The fourth molecule I have drawn is coming from the 1,4 addition to the alkene that I have drawn on the right. What you want to recognize with this one as well is that it is also a tertiary carbocation. So since I can initially generate tertiary carbocations, the most stable carbocations, whether I react the alkene on the left side of the molecule or the alkene on the right-hand side of the molecule, we will react both of them. And we will have this mixture of 4 different compounds if we actually run this reaction. So I want to look at another example. In this example, I'm going to have my conjugated diene. Again, we're going to make it nicely asymmetric, but I'm only going to have one group coming off of it. So notice we have lost the methyl group. I'm going to undergo the same reaction that we saw previously, but in this one, I am only going to get 2 products. I am not going to get 4 products. So again, we're only going to get these 2 products. I will not get a mixture of 4 products. So again, I recommend that you pause the video, you try to work through the mechanism to see why we are only getting 2 products this time instead of 4 products. So for these 2 products, they are both going to come from the same carbocation intermediate. and the carbocation intermediate that they are going to come from is going to be a reaction with the alkene on the right-hand side of the molecule. This produces for us a tertiary carbocation. The first molecule I have drawn is coming from the 1,2 addition. The second one is coming from the 1,4 addition. What you need to recognize with this one is that if I react the molecule on the left-hand side of the compound, I only have a secondary carbocation that is being produced. Through the resonance structures with the allylic carbocation, I then go to a primary carbocation, where when I reacted the one on the right-hand side of the molecule, I initially had a tertiary carbocation. So this, once again, we're going to base it off of stability. And what we're going to see is that I am not going to produce that secondary carbocation because I can produce the more stable tertiary carbocation. And that tertiary one will be the one that we form as the intermediate, which will be the one that will react to produce our products. So you do need to be careful with those asymmetric conjugated systems. And you need to watch for the carbocation stability, because that is what will also help you predict the products when you are dealing with an asymmetric structure. With our addition to our conjugated dienes, we also talk a little bit about kinetic versus thermodynamic control. This will allow us to, instead of producing an equal mixture of our compounds, it will allow us to favor either the 1,2 or the 1,4 product. So remember, kinetic control is really the one that is the product that we produce the fastest. Thermodynamic control is really the product that is the most stable. So under low temperature conditions, we end up getting the kinetic controlled conditions. We end up producing the fastest product that we can make. When we're under higher temperature conditions, we end up with the thermodynamic controlled product. And again, this is going to be the product that will be the most stable for us. So if we go back and we look at our initial conjugated, simplest conjugated diene that we can look at, and adding into it our HBr, we had our two products. We had the 1,2 product, we had our 1,4 product, when we looked at our two different species that we could make. So what we mean by our temperature control is if I run this reaction at 0 degrees, I'm going to produce, these are low temperatures, so the one that is going to be the most predominant in my mixture is going to be the one that I produce the fastest. The one that we produce the fastest is going to be that 1,2 compound. So under these reactions, I would have 71% of my mixture being the 1,2 product, where only 29% of my mixture will be the 1,4 product. You'll notice that we will make this compound the fastest because there's no resonance that I need to go through. The initial carbocation that we form is also going to be the initial one that reacts with the nucleophile. If I increase the temperature to 40 degrees, we will see a reversal in this. This is now going to be our thermodynamic control. And remember, thermodynamics is going to produce the most stable product. And in this scenario, the most stable product is the 1,4 product, because we see a change in the stability of the alkene. The alkene here is now an internal alkene. It's a disubstituted alkene, so it is more stable. Where that initial 1,2 product that we have has a less stable alkene. So we see a reversal in our percentages, and at 40 degrees Celsius, I would have the 1,2 product at 15%, and I would have the 1,4 product at 85%. So let's quickly look at a free energy diagram on kind of why this happens to our change in our controls. So they both start off with the same products, the conjugated system and the HBr. From here, they're both going to go to an intermediate. That intermediate is that initial carbocation. That initial carbocation that we have, it is going to react, and it is going to go down to our final product, where I have the Br in that 2 position. But then through resonance structures, we can also end up with the primary carbocation, please notice this primary carbocation is going to be a higher energy species for us. So we have a little bit higher of a transition state. But if we look at our final product, the final product is going to be more stable because we have the internal alkyne. So this is really our thermodynamic control that we would be looking at. Remember, thermodynamics kind of deals with equilibrium reactions. So what drives those reactions to completion is going to be the fact that the product is so much more stable, and to reverse that process is very, very difficult. Where the kinetic control works because it's going to be the fastest one for us. So it has a lower activation energy. It doesn't take as much energy to get to the final product that we have. So under low temperatures, where we don't have a lot of energy and motion with our particles, we're going to go that kinetics route. We're going to go the path of least resistance. When we have a lot more energy, we have the energy to get over that second high energy barrier with the primary carbocation to get to that more stable compound. Once we have established that more stable compound, to reverse that reaction, we don't have enough energy to do that. So through our changes in free energies of activations with the different intermediates that we can have is how we can control or predict kinetic control versus thermodynamic control.